Hello class, we will continue with the chapter which we started yesterday, that is efficiency of an algorithm. Okay, the name of the chapter is idea on algorithmic efficiency. That means we are trying to find out efficiency of an algorithm, how much efficient an algorithm is. And you must have watched the yesterday's video. In that I mentioned one or two small key terms like computational complexity. I used another term called big O notation. What is big O notation? Because that's the thing we are going to elaborate on in today's lecture. Big O notation is basically we write a capital O, and then within a bracket, within a function bracket, we write say how basically the input size how basically the performance of an algorithm varies. So we saw yesterday that if we wrote n square, okay, that means for an input size n, if n size input or n number of elements, whichever way you interpret it, if n is the input, n number of input is given to a program for which the algorithm is written, that algorithm will take n square number of steps at the most, n square number of steps to complete the problem or to solve the problem. Or we can say in a simple way that for n size of input, O n square, big O notation means the algorithm should take n square time. Now one clarification, I mentioned this yesterday, once again I am telling you, here the time and the steps do not mean what they mean actually literally, fine. Don't take the literal meaning, fine. Here n square number of steps doesn't mean the number of lines of the program. What does it mean? Yesterday I told you that if you take a for loop, okay, if you take a for loop, if the for loop includes statement 1, statement 2, statement 2, say the for loop works n times. So we can say here that for every iteration, for every round of the loop, statement 1, statement 2, statement 3 are executing. So if I imagine this to be my job profile, this to be a set of job, then this set of job are to be done n number of times. Okay, this set of job is to be done n number of times. So we can say there are n steps in that. Okay, step is taken because of that fact that how many times a particular process is going on. Or when we say n square amount of time, we need to say in comparison with another algorithm, how many steps are there in that and how many steps are there, how much time the other one will take and how much time this one will take. Okay, n square amount of time does not mean it is microsecond, millisecond or any unit of second. Don't think of the unit of a second here. It is time which is used in comparison with the time taken by another algorithm. Basically it means so. Okay, so we saw that. Now today basically what we are going to do, we are going to discuss a few problems, a few algorithms efficiency we are going to calculate. You have seen me doing one or two yesterday. But before that, let us do a small thing, let us do a small topic called dominant term. What is it? Dominant term. What is a dominant term? To understand this, I have to write an algorithm, fine. Or maybe I will write a small program, because algorithm is only implemented in a program. So I am writing a small program. The program doesn't mean anything, okay? It doesn't aim to do a particular thing. Suppose in a particular portion of the program, we have this particular algorithm is written, okay? What is the algorithm or what is the code written? Say I did somewhere x equal to x plus 1. I am doing the broken code, that is I am not writing the complete program. X equal to x plus 1. Then what happened? We took a for loop for an input size n. N is an input for the function or for the program, whatever you call it. For I in range 0 to n. Okay, or say I wrote I in range n. Fine. Now what I did, I took another loop for j in range also n. Okay, this was my loop. And here we had a statement say whatever, print say I multiplied by J. That was the job that I was doing. Fine. Maybe I was doing one more statement, say print. Say I was printing I. Then when this nested loop got over, I had another loop. For example, I had a K loop. For K in range, okay, these two also say what? N number of times. And what happened here, I did something else. Maybe I displayed print x many times. Once again, I am telling you, this program is not aimed to do a specific job. Imagine just at random, I just wrote some lines to make you understand what I mean to say by dominant term. Now, if I have to do, say, there is another line, say C equal to 0, just at the beginning. Fine. So basically, if I want to calculate the algorithmic efficiency of this particular algorithm or this particular portion of code, how do I do it? We can write that this is, say, taking a constant time is C0 amount of time. Okay. This one is also taking, because it doesn't matter how many times you execute the program. Every time you execute the program, this particular line will take every time same time to execute, because it's a simple. Here there is no variant term. X equal to x plus 1 means for any value of x, computation time will be same. So this one also says it takes constant time C1. Fine. Now you can easily make out, here we have two statements. Imagine this particular statement takes C3 amount of time, and say this one takes C4 amount of time. And this particular statement takes C5 amount of time. I'm just writing it short. So what did we finally get? If I now start computing, what did I get? I got total time as C0, okay? Then I got C1. Then here it's a nested loop. So what will happen? For every occurrence of J loop, okay, it will take C3 plus C4 amount of time. So C3 plus C4 amount of time. And since it is a nested loop, so we can write this multiplied by n, that much of time. And for this one, what will happen? This is also a simple for loop. Every occurrence of the loop takes C5 amount of time. So we can say C5 multiplied by n. So this is what is the total computation time of this algorithm. Now this can be written as, look at this, we can say, this can be written as this C0 and C1, maybe this is equal to, say, something like C14, right? And this one is equal to, say, C15. So we can write C15 n square, and then here we are getting C, say, 16 or C5 n. Let it be C5 n. So basically now what is happening is we got C15 n square plus C5 n plus C14. Now in this, what will happen? We can see here basically the algorithm time depends on two factors, n square and n. But imagine for a very large input, say the value of n is say 100. So 100 means we are getting here 100. This will become your n square. Okay, 10,000. So 10,000 will be a much higher quantity than 100 here. Imagine I made n equal to 5,000. So 5,000 square and 5,000. Don't you think that this quantity is becoming almost negligible in comparison to that? Now when we calculate the computational complexity or time complexity, it's an approximation what we do. It's not an exact calculation of time. It is just to understand whether an algorithm in comparison with another algorithm is a better algorithm or worse algorithm. That is what is the point here. So it's not exact calculation of time. It is an approximation of the time that we are calculating. So if we make an approximation, we can say that for very large input of n, this will become a negligible quantity. Therefore, we can say this thing, in Vigo notation, it is dependent mainly on n square. For a very large n, okay, what will happen? It will slowly we will see that it is getting dependent on n square. So basically what happens when a very big input is given to an algorithm, how the algorithm behaves, that basically decides its merit or demerit. So if I go for a very big input of n, what will happen? We will see slowly it will get dependent on n square. So approximately we can say it is dependent, the computational complexity of this particular algorithm would be O(n) square, or time complexity is O(n) square. Okay, so basically here n square will be called the dominant term. N square will be called a dominant term. So if you are given to write, explain what is dominant term, you can write a very simple example like this. You can choose an example of your own and you can write it. Fine. It need not be exactly this example. There are various ways of showing it, but it has to come finally in the formation of n square plus something into n plus a constant term. Then you can prove your point very nicely. Fine? Okay?